Yeah, sure. I'm Jack Szostak. I've recently moved to the University of Chicago about 2 years ago after being at Harvard and related places for the previous 40 years. I started off studying more biology, like DNA, recombination and telomeres. And over the years, I've gotten more interested in evolution, and now the origin of life is the focus of what we're doing. And I also enjoy, interacting with people in the biotech industry because it's a very exciting way to get technology out to help people. Yeah, the little special bits of DNA at the ends of chromosome, they're part of a very elaborate biochemical machinery to make sure the ends stay the way they're supposed to be. A lot of people are studying that now. So if you don't have this enzyme telomerase, which is what adds extra DNA to the ends, then the telomeres will get shorter and shorter. And so as cells go through more divisions, if there's not enough telomerase, the ends will shorten and eventually the cells will die. And this is a protective mechanism. It protects us against cancers because cancer in a tumor, cells are dividing and dividing and dividing. Eventually, normally, most of them die because their telomeres get too short. So in tumors that continue to grow, they start to make more of this enzyme. Now, in stem cells, right, the reason they don't last forever and one reason why as we get older, we're not so good at repairing our tissues and organs is, again, this fact that cells can only go through so many divisions. And so the idea has been around for a long time that if you could just make more telomerase, maybe we could live forever. But actually, we would probably all die of cancer. So it's not so simple, right? There's a very, very tricky balance. Yeah. A cancer is just cells which, for a variety of reasons, start to have uncontrolled growth. Right? So they just keep dividing and dividing. They don't pay any attention to the signals that say stop dividing. They just keep going, and eventually if that growth is not controlled, then we die. But most cancers, the vast majority of tumors die out, are killed by a combination of this probably telomerase mechanism, but also the immune system, when they're too small to bother us. It's only the rare ones that escape that control and cause problems. People have been trying to develop drugs that would prevent this undesired telomere elongation as a treatment for cancer. It hasn't been amazingly successful. There are still some clinical trials going on. People are still exploring ways to do it. We're still hoping that it will eventually lead to some therapies that will be helpful. But like many things in biology, it's not so simple, right? If you turn off this mechanism of telomere growth, then there are other mechanisms that kick in. So now you have to inhibit at least two pathways, or maybe three. So it hasn't turned into a fantastic cure for cancer. And in terms of aging, again, there's a lot of work going on. People are trying to understand, how you might affect the regulation of telomerase and telomeres. But like I was saying before, it's a dangerous thing to play with, right? So again, I think at this point, it's stimulated a lot of research. It's led to, decades of work on how telomeres actually work. It's led to explanations for some genetic diseases. And I think there's still hope that, some good practical things will come out eventually, but not really yet. So nowadays I've become much more focused on really fundamental scientific questions, like how did life get started, when our planet was young. That's, to me, it's both a fascinating question. I think everybody's wondered how we got here at some point. But I also think it's like a goldmine of interesting scientific questions. There's so many parts to that puzzle that, like any part of it that you approach, leads to interesting new science, new discoveries. It's a small field, but I have a lot of great colleagues working on different parts of this puzzle. So I really enjoy this kind of really fundamental work. Yeah, I think, kids are always curious about everything, right? That's one of the fundamental aspects of science, just being curious about how things work. Yeah, so, I find lots and lots of students are like super interested in these fundamental questions. Of course, we also like to do things that have more immediate benefit for humanity. So, there are opportunities to pursue fundamental questions and more applied questions, more biomedical research. I think it's really important to have the right balance of these two areas, and they're not separate, right? There's a continuum of things that go from the most basic questions like the origin of the universe or the origin of life, to things that are gradually have different applications, maybe long-term applications or maybe short-term applications. And you never know when something that seemed basic all of a sudden is going to lead to some exciting new application, right? So. Well, it's been very interesting being on this prize jury and seeing the variety of different areas. And I've visited Spain many times. I think one of the things that I like, apart from the wonderful environment and food and people, is that there really does seem to be a really broad appreciation of science, more than you see in many other countries. So I really like that. Well, the money to support most science comes from the government, right? So it's really important to have communication between people in science policy or science funding and the scientists doing the work and deciding what the priorities are. It's also, of course, nice when there's private philanthropy to support science. Right. No, that's a really good point. If we want the politicians to fund more fundamental research, they have to know that people want that. And that means we have to explain to people that the practical discoveries always come from more fundamental underlying questions, right? I mean, I've worked on many things in my lab purely out of curiosity, and they turned out to be, you know, usually completely unexpectedly, to be really interesting, and sometimes have had, you know, actual practical applications. We had done some of the early work in my lab on how to evolve molecules to do what you want. And that led to founding several companies. One company was bought out several years ago for $2 billion. So it actually had drugs in clinical trials, all of which came from work 30 years previously, you know, trying to just understand the basics of evolution. So the more we can get across the message that the really basic questions, even though you don't know where it's going to lead, that's the source of all the innovation that leads to advances in science and medicine. I think, you know, having videos, TV shows, you know, websites for popularizing science is really important. So in the US, we have this biomedical research foundation called the Howard Hughes Medical Institute. And what they mostly do is they just support science. They identify people doing interesting work and they support their money. But they've become very active recently in this kind of public outreach. And they've even hired people whose full-time job is making films about scientific advances to communicate to the whole world. So I totally agree. It's really important to do that. It is very challenging. I think astronomers and you know, rocket scientists have it easy because they have such spectacular pictures to show, and you know, it's very it's something everyone can understand. You know, going to space, exploring our solar system, seeing the stars. It's a little harder to get people excited about some other parts of science. I think biology and medicine, you know, everyone understands the importance of medicine, so that's a good starting point. What I'm doing now is chemistry. That's really hard to communicate with people, right? So yeah, I do struggle with that. You know, I don't really, I think, appreciate or understand the importance of science communication. But I think that culture is changing. I think, you know, all the young people understand this, and I think a lot of older people like me also understand it. And you know, so being on this prize jury is relevant. So you know, I think the best thing about the Nobel Prizes is that it's science communication to the public, right? I mean, they're incredibly popular, especially in Europe and especially in Sweden, right? Everybody knows about them. And it's a way to get out there to people and explain, you know, what interesting, you know, what might seem like some obscure discovery is actually really important. So actually not that much. I mean, it was made for a very busy year that year, so always a lot of invitations to do things. But I was still deeply engaged in doing science, and I still am. So that is still 90% of my life. It's just being in my lab, working with my students, talking to other scientists, my collaborators. And, you know, I like doing things like this visit and but most of what I do is actually still doing science. So it didn't change my life all that much. So I think you know, it's nice to recognize people who've done something really significant. So I think that's a good thing. But the bigger purpose, I think, is to tell people about it, right? I think that's why it's worthwhile having these. You know, if it was just you know, rewarding people for doing something, I think that's not why we do science anyway, right? It's the purpose of these kinds of awards really should be just to communicate what it's all about to a broader audience. Yeah, I think what I always like to tell young people is, you know, science is fun, it's interesting. If you're lucky and passionate about it, you can discover things that turn out to be really important, either in terms of helping people soon or just in terms of making basic discoveries. So I just think it's the most interesting thing you can do.